In part 1 of this video series on redesigning the shape of an air duct, I used Fluent's Adjoint solver to calculate sensitivity data for an observable that included both the pressure drop between the inlet and outlet, as well as the uniformity of the outlet velocity. Having run the Adjoint solver, now is a good time to save the case and data file with a new name. Shape optimization problems are often an iterative process, so it is good to have files for each solution. I will now proceed to use the Adjoint results to modify the shape of the mesh using the Adjoint Design tool. To begin, I will define the objective of the mesh change. I want to see an improvement in the observable for the pressure drop and velocity uniformity, and I'll specify a targeted change that reduces the value by 10%. The negative sign here indicates that I want a reduction. Note that a 10% change is relatively aggressive, but is suitable in this particular case. Now, if I had not previously combined my multiple observables into a single one, I would want to import the sensitivity data here from the separate Adjoint solver calculations and set up additional objectives. I want the deformation region to encompass the entire mesh, so I'll start by defining a box that is sized to fit the wall. The graphics window shows the box in light blue, and I will enlarge the box so that there is a comfortable margin around the mesh so that it is not overly constrained. As part of the region conditions, I'll increase the number of control points in each direction, as I've defined a relatively large deformation region, and I want the control point density to be high enough to allow changes to be made to the mesh at a small spatial scale. I'll keep the default continuity settings. The Design Conditions tab allows me to constrain or prescribe the mesh deformation. In this case, I want the mesh to stay within the bounds of surfaces that represent other geometrical components that surround the air duct. I will bound the wall surface, and will import the bounding surface from an STL file, which was generated by a separate CAD software package, though Fluent Mesh and case files could also be imported here. I'll select and display the surfaces in the graphics window. It is important to verify that the orientation of the bounding surface is appropriate. Here we see that the arrows indicate that the mesh will be constrained to be outside of the bounding surfaces, which is the opposite of what I would like. So I will reverse the orientation. As you can see, the air duct already violates the bounding surfaces, so these regions will be adjusted, and then the mesh will be allowed to further deform within this green packaging space. I will use the default numerics for the most part, since these values are suitable for a variety of cases. However, I will increase the preconditioning of the freeform motion, as this is recommended when using the bounded by surfaces design condition. Back in the Design Change tab, I will specify that only the wall of the duct will be modified, and not the inlet and outlet, and I'll select the bounding condition I created. If I had not combined my observables prior to the Adjoint solution, I would specify the weighting of each of the multiple objectives in this field. It's a good practice to check if my setup will produce good results. Here I see that while there are possible conflicts between the condition and constraints, there are none that are fatal, so I can proceed. Now I can calculate a design change to optimize the mesh. Results will be printed in the console as it processes, and when the calculation is complete, the expected change will be displayed here. Since the objective is decreasing as I intended, I will proceed to modify the mesh according to the calculated design change. I'll display the modified mesh. Note that if the resulting mesh were not satisfactory, I could revert the mesh change. If the results are what I want, I have the option of exporting the modified mesh surfaces as an STL file for use by other CAD software packages. At this point, I could now rerun the general Fluent solver and see how much the pressure drop and the outlet velocity uniformity actually improved for the modified mesh. With such results, I could then go through the entire process again, that is, run the Adjoint solver for the changed mesh, calculate an additional design change, and modify the mesh again. By repeating this process, I will incrementally move the design toward an optimal shape. I've run this particular air duct through 30 Adjoint mesh modifications, and you can see here how the shape of the mesh changed by this process. The following animations show the changes in the observables. Here you can see how the pressure difference between the inlet and the outlet is reduced as the design is changed. And here you can see how the velocity at the outlet becomes more uniform. This concludes this demonstration of using the Fluent Adjoint solver to optimize the shape of a mesh.